If I can have your attention, please.
If he could have our
Thanks.
attention.
We're going to be talking today and part of the day tomorrow about Vesper Theory. This is one of those funny chemistry things where the letters are all there, but they're in not the right order. We still call it Vesper Theory, though. Vesper. Standing for valence shell electron pair repulsion. When you have a molecule, you have a central atom in the molecule, and then the peripheral atoms are coming off of the central atom. The bonds that are being made are electron clouds to those peripheral atoms. Those electron clouds don't like one another. So the atoms will try to spread themselves as far apart around the central atom as they can get, so that they can minimize that repulsion. I'm going to be describing Vesper Theory in an order. The order is going to be based on what I call the coordination number, and that's the number of things around the central atom. So that's what the definition I'm giving down here is. The coordination number is going to be, when you have the central atom, the number of atoms attached to the central atom, plus the number of lone pairs on the central atom. Because the lone pair is a pair of electrons in there that will repel the others, the other pairs of electrons that are making bonds. So they definitely deserve to be recognized in the coordination number. Now I'm going to start with the smallest coordination numbers to go up. We're going to go from coordination numbers of 2 up to coordination number of 6. And I'm going to get as far as 5 today. I'm hoping to be able to do one molecule with a coordination number of 5, and then we'll quit. I'm not going to do BEF2. In the interest of time, I'm just going to jump to CO2 and start there. Okay? I'll remind you, we have a reading quiz tomorrow. Did I remind you that already? No. Spencer was complaining about that.
Kill it like orders.
Yeah,
How about like we
should have had the reading quiz today.
That's what I was complaining about.
Yeah, but then you wouldn't read.
Yeah.
I would have.
I would have.
Actually, no. Wait, if it was a reading quiz, I would have read.
Oh, okay. Why don't you tell me that then?
Wait.
Anyway, next week we're going to do the same thing. We're going to have a review quiz on Monday, and then reading quiz on Tuesday.
You're killing me.
Then we'll be done with those review and reading quizzes.
Wait, that's it?
There's the only quiz we're going to have for the
Don't you guys?
What's the point of those review quizzes?
We have a chapter 8 and 9 quiz.
ready for the AP.
What's that,
I
guys?
feel like we accomplished nothing from those review quizzes.
You're being recorded.
Yeah, this is.
Is it new test? They're hard.
We still need to know the concepts.
Well,
And that's the whole idea of the review quiz, is to get you looking at problems similar to what we might expect on the AP exam. I don't know really what to expect with any certainty at all.
Should we get a Barron's book or something?
I would recommend it, yeah.
Can we like beg the
It
college
is.
force to just give us
Going over the
5s?
test is hard.
You're gonna probably have Adi coming after school and letting you about the entire test.
Maybe so. All right, well, let's get to this. We're going to be looking at shapes of molecules, starting with the simpler ones where there's not a whole lot around the central atom, building up to the point where we have a lot of things around the central atom. In fact, because I'm having Eman record, I'm going to just go ahead and do the work over here. If you wanted to write this down, have you written it already? Definition of Vesper theory and coordination number. Let's start with CO2. As a reminder, carbon dioxide has a Lewis dot structure that we're going to have to do several steps to be able to figure out. I'll go through them quickly just to bring it all back to you. Count the number of valence electrons. Carbon has 4. There's 2 oxygens that each have 6. So 4 plus 12 is 16 electrons should be in the structure of CO2. Find the one that's the least electronegative. Almost always is written first in the formula. So that one will go in. Then we have 2 oxygens. Attach them first with just single bonds, unless you know otherwise. And then after you have single bonds to your peripheral atoms, then you're going to get 8 electrons around everybody. That's called the octet rule. Count the number of electrons once you have 8 around everybody. Hopefully the number of electrons is equal to that number, and then if that's the case, then you're done.
No.
It's not going to be the case though. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 20 electrons, but we can only have 16 in the structure. So we have to make double bonds. So make a double bond between the C and that O. Now if you count them, there's 18 electrons. We're closer, but we're not at 16. So you need to make another double bond. Now you could make a triple bond there and leave that as a single bond. Most of the time though, we'll express CO2 as 2 double bonds, like that. So the carbon doesn't have any lone pairs around it. But it's got 8 electrons around it, 2 pairs there and 2 pairs there. Okay, so we would consider the coordination number of the carbon to be 2 in this case. It's got an oxygen attached to it there, an oxygen attached to it there. That's got 2 atoms on it. The number of bonds doesn't matter so much. So the coordination number is not referring to how many bonds are being made. It's referring to how many atoms are attached to it.
Or if you made a double bond, you took off letter C and one.
Yeah, when you have to make a double bond, you're going to remove a lone pair from both adjacent atoms and just replace it with a shared pair of electrons. I have just a simple model to help us to picture what the shapes of these things are going to look like. I've got styrofoam balls. The one with a little bit of black spray paint on it, I'm going to use as the central atom for all these molecules. So now when we have CO2, you've got a carbon in the middle with the 2 oxygens on it. Vesper theory says that the 2 oxygens should be as far apart from one another as possible. Now, does this look like a reasonable structure of CO2?
No.
Vesper theory says that they're repelling one another, so they try to spread out. What's more like it? It's more like it if they arrange themselves. This isn't stuck in there very well, like that. This is as far apart as these bonds can get from one another. That is a pair of electrons, and that's a pair of electrons. They don't like each other. They're going to get as far apart from each other as they can be. So this is the structure of a CO2 molecule. Yeah? What's the shape of that?
Linear.
It's linear.
Dumbbell.
Right. Not a dumbbell shape. That would be a dumbbell where you got the handle in the middle, right? And then the bulging sides on the outside. But
A very weird dumbbell.
yeah. But anyway, we would call that shape linear. So the CO2 is a linear molecule.
It's a shape.
The angle of the bonds. I don't know what just happened.
So, Laura, do you know what a shake weight is?
A shake weight? Yeah.
SC
I missed it too, yeah. This is being recorded and I just totally missed out on that one. What are you laughing at? You don't want to say?
Shake weights.
Search it up later.
I know what a shake weight is, don't I?
The point is,
What's that?
It's a South Park episode.
Oh, yeah, see, you lost me. Okay. Anyway, we go back to this. What is the angle between the 2 bonds?
180.
It's 180 degrees, yeah. When you have a straight line from there over to there, it's 180 degrees. So the bond angle and the shape of the molecule turn out to be pretty significantly important. And it has to do with when we start determining what the properties of molecules and justifying properties of molecules, like why water is a liquid. Why CCl4 is very heavy, but it's a liquid and not a solid, that kind of thing. It has to do with shapes of molecules. And why some things are polar and some things are not polar has to do with their shape. So the shape does matter a lot. Anytime you have a coordination number of 2, you have a linear molecule. Anytime. No matter what the molecule is, if its coordination number is 2. Spencer, let's go to the next one. And that's going to go to the coordination number of 3. We're going to have a couple of different shapes when we have a coordination number of 3. I'll just do them in line here. This is H2CO, the formaldehyde molecule. Going through the, go ahead.
Might sound like a stupid question, but it's like, why is it coordination number 3?
Oh, we'll see that in a second. You wouldn't just look at the formula and know that automatically. Do the dot structure first, and then you'll know how it's coordination number 3. So you got 2 electrons there, plus carbon has 4, plus oxygen has 6. 2 plus 4 plus 6 is 12.
Oh, it depends on their valence electrons.
The coordination number? No, it has to do with the little structure.
Oh,
You have to get the Lewis structure to determine the Lewis coordination.
Is that why we're doing 800 Lewis
I
structures?
remember something you have to
this
like count the
chapter?
lone pairs in order to figure out some sort of shape or
that's
whatnot.
like hybridization.
Or something else.
Yeah, and that comes in this too. You'll see it. So the H2CO looks like this. You got the carbon in the middle, that's the least electronegative element. Oxygen, hydrogen, hydrogen. They don't get any lone pairs, so we need our lone pairs around them. 2, 4, 6, 8, 10, 12, 14 electrons represented here, but we should only have 12. So we need to get rid of 2 electrons. Yep, and make a double bond. So after doing the Lewis structure, now we see that the carbon is attached to 3 elements. And it doesn't have any lone pairs on it. Therefore, the shape of, or the coordination number is 3. Farouk?
How can we not tell from the chemical formula that it's connected to 3 different elements?
You don't know how many lone pairs are on the central atom until you do the Lewis, though.
Oh, so if carbon had 1 lone pair, it would be 4.
Yes,
Oh.
yes. And that's why this one is going to turn out to be a coordination number of 3 as well. HNO, when you look at HNO, oh, there must be a coordination number of 2. That's not necessarily true because it turns out that N has a lone pair, which counts for the coordination number.
Oh.
All right, so coordination number 3, you got 1, 2, 3 atoms on it. Now, if I do this shape, the same as the
Hush.
if I do this the same as the dot structure, I have the carbon bonded to the O there, the H there, and then an H there. Is that really the way that H2CO looks?
No.
This reflects the dot structure, but that's not at all. It turns out, according to Vesper theory, yes, these 3 bonds are spread out as far from each other as they can get. Are they spread out right now as far from each other as they can get? No. How would they get farther apart?
120 degrees.
Yeah, right, like this.
Are they all equally spaced or?
Yeah,
For this one.
even though they're different sized atoms, space them equally as far apart. It doesn't matter that one is a double bond. We're going to address that later on, but not right now. The shape really does not depend on whether they're double or single or triple bonds. All it depends on is how many things are around the central atom, including lone pairs. So this has 3 things around it. They're going to spread out like that. What's the shape?
Tetra.
No, trigonal planar.
Trig-
Yeah, all 4 of these atoms lie in the same plane. And therefore, this would be a planar molecule. Since it makes the shape of a triangle, we call it trigonal plane.
That's a 20?
Trigonal.
Yeah.
That sounds so cool.
Oops.
We learned it last year.
I don't remember trigonal.
Yeah, you did this last
Yeah,
year
but
for
they
sure.
were like 3D.
Yeah, but that was Mr. Hubble.
What's the angle of the bonds?
120.
It's 120 degrees.
I like that.
Yeah. But we're not doing that now. We'll do hybridization another time.
Okay.
So that would be the shape of the H2CO molecule. Trigonal planar. Some people call that trigonal planar. It's not, it's trigonal. I don't know how that's difficult, but it's trigonal. Okay?
Trigonal.
Take your shot. The next one we're going to do is HNO. HNO looks like this. The N has a double bond reaction. I'm just going to fast forward through this. I trust that you can do dot structures by now, and if you can't, you need a lot of practice, and there's plenty provided.
You just wing that?
Problem.
He knows.
Well, this is the 3rd time today I've done that.
Oh.
Well, I think it's the bazillionth time in my life that I've done that, so I have no idea.
It's okay.
So there is a double bond between the N and the O to give everybody 8 electrons, and they have the right number of electrons total in this thing. So what is the coordination number of this molecule?
3.
1, 2, and 3. That lone pair does count. That means
You're
that
so
the
smart.
N has 3 orbitals that are spreading apart from one another.
Then
Now,
just take one of them.
this has a central atom with 3 things apart. I'm going to leave the toothpick, but take the styrofoam ball off of it. That toothpick is there to represent there is still a pair of electrons up there. The N has the double bond of the oxygen, the single bond of the hydrogen, and it's being still, they don't just kind of come out to a straight line. The repulsion of this lone pair still keeps those down at that 120 or so degree angle. But the angle is not 120 degrees. Anybody remember from Chem 1 what happens with this?
They bend.
The shape is called bent,
109.
but what is the angle between these two? It's not 105.
109.5.
Not 105.